Recall that there is no product or quotient rule for integrals, but there is a version of chain rule, sort of. If you recall what chain rule is, the derivative of a composite function, f of g of x, is the derivative of the outside, f prime of g of x, times the derivative of the inside. Now, if we're working backwards, if you see sort of the f prime of g of x times g prime of x under the integral, then you can use this technique called U-substitution. So what you will see is something of this sort. If you have an integral of 2x cubed plus 1 to the 4th power times 6x squared dx, it's a little hard to recognize this as chain rule. But if you notice that if you have the f prime of g of x, basically if you have the inside function, a function within an exponent or exponential function, times sometimes the derivative of a version of the derivative of what's the inside. So in general, you do not want to, you will not be able to integrate it directly without expanding the 4th power, which can get very challenging and difficult and time consuming. So what we can do is use a substitution. So this is the way without integrating it directly. So here's what we usually do. If we let u, for example, that's why we call it U-substitution, if we let u to be the inside function, which is usually the case, so the inside function inside of the exponent is 2x cubed plus 1, okay? So if we do that, then you can find the derivative of this u. Just differentiate, so disregard the integral before, but if we differentiate the u, what will we get? Well, differentiate with u with respect to x, you'll get du over dx equals to derivative of 2x cubed, that's 6x squared. The 1 is just a constant, so that will give us 0. And notice there was a 6x squared inside of the integral, if you recall, so there is the derivative of this du. What we need to do now is multiply both sides by dx, literally. So we'll get du equals to 6x squared times dx, because when we substitute, we need to substitution to match exactly. Okay, this is what I usually do. I look for, so to perform the substitution, this is how I have it written out. So 2x cubed plus 1, this is your u. 6x squared times dx, that whole thing is du. And so we substitute. And notice in the new integral, that's all you have is u. You don't have anything else. So you have u to the 4th times du. Now note how we made the integral a lot simpler than before. U to the 4th power is a lot easier to integrate than what we had before. So what we do next, the next part is the integration piece. Okay? So as soon as we integrate, now note that the integral sign is gone. So the antiderivative of u to the 4th is u to the 5th over 5 plus a constant. So notice you don't need the integral sign, you don't need the du. The du is like the derivative portion of the integral. So as soon as you integrate, you don't need the du portion or the integral sign. So you just have the antiderivative plus a constant. So again, I'll probably be repeating that quite a few times. But anyway, so we got the u, and at the end we substitute back. So we'll get the answer as 2x cubed plus 1 to the 5th over 5 plus a constant, and that is your final answer for the indefinite integral, which will compare it to the definite integrals in section 7.4 coming up. Okay, so this technique only works if we have the derivative of the inside function within the integrand, or the function that we're trying to integrate it. Sometimes you have an extra constant in there that doesn't match exactly, but we'll learn how to deal with that. Here is the next example. What if we have 4 times 2x plus 3 to the 4th power dx? So again, let's try this. Let u be the inside function, which is 2x plus 3. We'll take the derivative of u. This is how I'm going to do it from now on. Derivative of u is du equals to derivative of 2x is just 2. 3 is gone, but we always attach the dx at the end so we can match the dx from the integral. Okay, so instead of multiplying it, that kind of saves us an extra step. Now notice we have 2 dx for the du, but then in the original integral we have 4 times dx, the 4 on the outside. So that does not match. So what can we do? Well, to modify this, whenever you don't match exactly, you divide by the constant that you have. Du equals 2 dx, divide both sides by 2. Now you have 1/2 times du. That's what you're going to substitute for the dx. And then that's going to multiply with a 4 and so on. So here's what we're going to do. We're going to substitute exactly. So we keep the 4. That's your constant. So we keep that. The 2x plus 3 to the 4th power, that was u to the 4th power, times the dx was 1/2 du. Remember how we divided by 2. So we multiply literally by 1/2 times du. So the 4 can multiply with the 1/2, which will give us 2 u to the 4th du. So see how you can modify this at the end, even if it doesn't match exactly up to a constant. So now we are ready. As soon as you simplify this integral with the u, you can integrate. So sometimes you substitute first, simplify if needed, and then you integrate it. So as soon as you integrate it, notice the integral sign is gone. We keep the 2, that's your constant, times u to the 5th over 5 plus c, which we can substitute back for the u. So we get 2 times 2x plus 3 to the 5th over 5 plus a constant. That's how it works. So let's see more examples. What if we have something complicated looking like this ratio right here, which is 2 times dm over 2m plus 1 cubed? Well, we can do the same thing here. So 2m plus 1 cubed, that's the one we're going to substitute for. Again, the inside function is u, 2m plus 1. Take the derivative of u, which is du, equals to 2. The m is gone, but we have the dm. If you notice, we're going to keep the same variable. The 1 is gone because that's a constant. Now notice, we do have 2 times dm in the numerator, so it does match exactly. So 2 times dm, that's du, to 2m plus 1 cubed in denominator, that's u cubed, and that's our substitution. That's equals to u to the negative 3rd power. We have to do that to use the power rule. Bring that up. So now we can integrate it and back substitute. So u to the negative 3, we can use the power rule. So increase the power by 1. So we get u to the negative 2 divided by negative 2 plus a constant, which if you ever divide by negative, usually I pull that out on the front of the function. So we get 2m plus 1 to the negative 2 power divided by 2 plus a constant. Don't worry too much about negative exponents in this section. I think you can leave them in if needed. Okay, the next example is very similar if you have x squared plus 2x minus 4. But let's take a look how that works. If we take the derivative, we're getting 2x plus 2. Don't forget times the dx. So I put that in parentheses just to make sure we're multiplying. It does match exactly again. So now I believe we can substitute. So notice how 2x plus 2 and the dx are both du. So I just put du on the top, divided by u to the 4th, which again is u to the negative 4th, just as before, which if you integrate, you'll get u to the negative 3 over negative 3 plus a constant. And again, we can pull the negative on the outside, and we back substitute x squared plus 2x minus 4. So it works very similar. Let's take a look how it works with exponential in our next example. So with exponentials, if you recall, the inside function is usually the exponent, which notice 2x cubed, and how we have the x squared on the outside. We'll see how that works. So the inside function, again, let's let the whole exponent, u equals to 2x cubed. Let's take the derivative of the u, which will get du equals to 2 times 3, that's 6, x squared, and we attach the dx. Notice here we have 6, in the integral we have 3. Once again, it doesn't match exactly, but that's okay. If it doesn't match, we divide both sides by 6. That's how I get 1/6 du equals x squared times dx. So this is how I like to modify it. So when we perform the substitution, so here's what I like to do. The 3 we keep, that's our constant. The x squared, that's actually our 1/6. So notice sometimes I put 1/6 right next to the 3. which would have made sense. But again, because x squared times dx was 1/6 du, that's how we perform this substitution right here. So we have 3, it becomes e to the u. The x squared and the dx became 1/6 du, okay, literally. And then 3 times 1/6, that becomes 1/2, and it becomes 1/2 e to the u du, okay? So then later, 1/2 e to the u. So to integrate it, we keep the 1/2. Recall that the integral of e to the u, that's just itself, e to the u plus a constant, and then we can substitute back, and that's 1/2 e to the 2x cubed plus a constant, okay? So the next one is another exponential, very similar. Again, we can let the u equal to the exponent 2t minus t squared. Take the derivative of the u, so we're getting 2 minus 2t times dt. Really, I should have put parentheses, but it's the same kind of idea. But then, again, it doesn't match exactly with a 1 minus t, but notice how you can factor out the 2. So you'll get 1 minus t dt. So now it matches exactly, divide by a half. Okay, so when we substitute, so again, we have 1 minus t, that's really a half. I could have put a half, but 1 minus t times dt, that becomes 1/2 du. And e to the 2t minus t squared, that becomes e to the u. So it basically becomes 1/2 e to the u again. And again, the answer is e to the 2t minus t squared over 2 plus a constant. Sorry, divided by 2. Okay, and now let's look maybe at the quick application. When would we need u substitution? Well, here we have the marginal revenue, which is r prime of x equals to 4x times x squared plus 27,000 to the negative 2/3 power. That's in thousands of dollars. So the total revenue from the function from 125 players is 29,591. So we'll get back to that when we need that. So we need to find the total revenue. So to find the total revenue, we need to integrate. And when we integrate, we're going to use u substitution again as before. We can use the inside function for the u, x squared plus 27,000. Then take the derivative, so we get du equals to derivative of x squared is 2x times dx, okay? Again, there was a 4 in the original, so we have to divide by 2, both sides by 2, so get x times dx, and let us substitute. So 4, again, instead of the x, I just put the 1/2 times u to the negative 2/3 power, and then the dx becomes the du. So again, that x was a constant. So I am substituting exactly, if you notice. So the x, I substituted 1/2. For the dx, I substituted the du. That's how I break them up sometimes. So 4 times 1/2 is 2. And then u to the negative 2/3. And so with rational exponents, the same idea. You increase them by 1. So we'll have 2u to the 1/3 power. Negative 2/3 plus 1 is 1/3. Divided by 1/3 plus a constant. 2 divided by 1/3 is the same as 2 times 3. So that's 6u to the 1/3 plus a constant. And at the end, we substitute back. That's x squared plus 27,000. Now notice we do have to solve for the constant at the end. This is where you had to recall the units, which sometimes are the case. So revenue from 125 players is 29,000, but because it was in thousands of dollars, it's like 5,000 is the same as 5, and then you can write out 1,000. So notice we can divide by 1,000, 29.591. So don't forget to do that, otherwise your answer may be quite a bit off. So we set that equal to, so I plugged in 125 inside. Using my calculator, I got 209.591 for the whole thing plus a constant. And to solve for the constant, we can subtract 209.591 from both sides. So I got negative 180 about, and that was our constant. And that's the revenue. And that's it for this section. I think the next one is just algebra, where you set the equation equal to 40 and you solve for it. I'm just gonna show you guys what's happening here. And I'm using some algebra. Add the 180, divide by 6, cube it to get rid of the 1/3, and basically use some algebra to say how many players must be sold if the revenue is at least 40,000. And that's it for this section.